Okay, we're going to be looking at part 2 of chapter 6, which is about momentum conservation and collisions. So, when you have momentum conservation, the idea is that you are conserving something. And this is your first big conservation law. We kind of talked about conservation of mass before. Conservation of mass is where you end up with the same mass that you started with, right? So we talked about that when we talked about the nature of science and the scientific method. So that's a law of conservation of mass. Um, so the same thing, this is the law of conservation of momentum. Remember that laws are observations about the rules of nature. You don't have to explain them, although they can be explained eventually. But the idea is that this is something serious. This is the law, and so the idea is that the momentum of a system of objects cannot change unless it is acted on by external forces. So remember we talked about a system of objects, how you could outline it with a box. So let's say I outline this kid in a box in his wagon. Okay, so there, the system of objects is the kid and the wagon. Now, therefore, the parent over here is providing an external force. So the kid in the wagon can't make the wagon move all by himself. It's like if you're in a car, you can hop out of a car and give it a push to make it go. But what if you just try pushing on the um, the dashboard? You're applying a force. So why doesn't it work? Why won't the car go? And the reason for that is that just like this kid here, he can push on the wagon. And if you were in a car and you decided to just push on the dashboard, okay, so you're pushing with your hands forward. But what's happening to the rest of your body? Where are you getting that force from? Well, as you push forward hard on the car, your bottom pushes back on the seat on the car too. And those two forces are going to cancel out. Those are internal forces. So the car is not going to change its motion by you just pushing on the dashboard. You've got to get out and push onto the trunk, right? And remember, then your feet are making contact with the ground. So you push backwards on the ground as your hands push forward on the car. And so you are getting an external force because, of course, the reaction force of the ground pushes your feet forward, and that's the force that you use to push the car forward. So, internal forces don't accelerate systems, but external forces do. Okay, now, if there are no external forces, then the momentum of a system will stay the same before and after any interaction. So let's say the kid is in the wagon and he's sitting still. Well, if nobody pushes the wagon, he's just going to stay in the wagon and he's not going to be able to move it. Now, you've seen kids scooch themselves along, but that's because they're using they push down and against the earth. Okay, so pretend they can't do that. So in this wagon, he's isolated from the earth. So in that case, he wouldn't be able to make it move. It would be like a frictionless surface. Um, now, so we need that external force to change the momentum. And let's say he was moving. So his wagon is rolling across the ground freely. Well, what stops the wagon? Friction, right? Running into something. Those are forces. Like Galileo said, if there are no forces, that wagon could go forever. So this conservation of momentum idea relates back to Galileo's idea of inertias and Newton's first law. Okay, now, so we say momentum is conserved. It doesn't change before and after the interaction. Okay, so let's go look at a system of objects. And here's a formula for this. The idea is that, again, in the absence of an external force, the total momentum of a system remains unchanged. That's the law of conservation of momentum. And so as an equation, you could get the total momentum before an interaction and the total momentum after, and they should remain the same if it's a really isolated system. Now, how do we get the total momentum of a system? Well, we just add up the momentums of all the objects in the system. So if you're trying to imagine what I'm talking about, think about balls hitting each other, okay? And they will bounce off, right? Or maybe one hits and pushes the other one in the other direction. So the thing is that the total momentum of the system will remain the same after this interaction if all there are these two balls in our system. Okay. Okay, so let's look at collisions. Now, Newton needed to test this, by the way. So what he did was he actually invented what's called the Newton collider. So let's go look at the Newton colliders. We'll look at it in a second. Let's do a little bit of playing around here. So this is, of course, is the game of roller derby. And only women get to play it, and they get to push on each other. And in fact, they do a lot of interesting collisions in roller derby where they share momentum. So a team will share its momentum with one person to give them more speed. Because that's something. The team has a certain amount of momentum, but they can transfer it to one of the players. Okay, so they push each other, and that transfers momentum. So that's what we call a collision, that transfer of momentum when objects push on each other. So when objects collide in the absence of external forces, the total momentum before the collision equals the total momentum after the collision. And let's just look at these balls here. And so this would be the before. We've got the black 8 ball coming in and hitting the blue 2 ball, which is sitting still. And afterwards, we have the black 8 ball has bounced backwards, and the blue ball is moving forward at 3 meters per second. Okay, now let's check to see if the momentum is conserved in this case. So for total momentum, we need a mass 1 times velocity 1, the momentum of the first ball, which is going to be the 8 ball. And then we need to add to it the mass of the second ball times the velocity of the second ball. And then afterwards, we're going to do it again, but now we're going to look at the velocity 1 final. And the masses haven't changed, just the velocities. So we need to know what those final velocities are, which we have. Now those should stay the same. Now the ball, I'm going to make 0.2 kilograms because a lot of balls are around that mass. Okay, so all the balls are going to make the same mass. So let's see what happens. Our 8 ball, we've got 0.2 kilograms times the velocity, which was 2 meters per second. Okay, for the second ball, we've got 0.2 kilograms, but it's times 0. The ball isn't moving. Okay, so 0.2 times 2, that makes 0.4. 0.2 times 0 is 0. I know you're tempted. People often try to put like 0.2. They don't want to accept that that ball is just a 0. And it is. It's got no motion. It has no momentum. So no velocity, no momentum. So it brings nothing to the party here. And so our total momentum is all due to the 8 ball. And so our total momentum is 0.4, and that will come out in kilograms meters per second. Okay, so we've got the momentum on one side. Let's look at the other side. All right, now the mass is the same, 0.2, and the final velocity of this one is -1. Remember what minus means in physics? Other direction. So the ball has bounced backwards. And then we've got 0.2 times 3. So on this side, we're going to get a minus 0.2 plus 0.6. When we add those together, we have 0.4 kilogram meters per second. So we have the same value for the momentum before and the momentum afterwards. We have proved that momentum is the same on each side here. So momentum, we would say, is conserved. Okay, now elastic collisions happen between very hard objects, which is weird because most of us think of elastic things as soft, stretchy things. But that's not what scientists meant. When they said elastic, they were talking about playthings where the shape doesn't deform. It comes back to its original shape. And so harder things actually have more, they will come back closer to their original shape. And even bouncy balls, I've got some balls here, but the hardest one is the bounciest one, right? Bouncy balls are usually harder than softer balls, or like a tennis ball. You want a good bounce, you don't want a soft tennis ball or a soft basketball. You want the hard one, right? That will give you better bounce. So anyway, the idea is they don't lose energy by generating heat. When something gets deformed, the molecules move past each other and it generates heat. You get friction. And so as they stay undeformed, then you've got a better chance of having the energy conserved as well as the momentum. So momentum and energy are conserved. And we'll be talking about energy in future chapters. So a bowling ball hitting a bunch of pins, it comes in with some momentum, and then it scatters and transfers that momentum to the pins, right? They have smaller masses maybe, and they'll each take a little bit of the momentum from the bowling ball, and so it might come to a stop. Okay, or it might go on to where it has to get caught. But the idea is it transfers momentum to all these objects that it collides to. And some of them collide with other ones, and so more momentum gets transferred. And so all around us, all the time, momentum gets transferred to different objects during a collision. So when you've got elastic collisions, the energy can transfer very efficiently. So here we've got a green ball coming in. So think about playing pool. And so here's a pool ball coming in, the green one, it hits this yellow ball. That's the before. They collide. Afterwards, the green ball is now at rest and the yellow ball goes shooting off. Okay, now the second situation, we've got the green ball and the yellow ball both moving, but they're moving towards each other with equal speeds. They collide in the center and they go off, they bounce off and go at equal speeds going off. In the third situation, C, we've got the green ball going fast. It overtakes the yellow ball, which was moving slowly. And one overtakes the other. They collide. The green ball now has less momentum. The yellow ball has more. In these cases, it's like they transferred their momentum totally to the other ball, which can happen when the masses are equal, that you can just transfer the momentum. Okay, so let's go look at this live, because Newton invented what's called the Newton collider so that he could examine this. So you've probably seen Newton colliders before. Maybe you've played with one, right? So you've played with this before. Okay, so I'm going to give you a different view here. You're going to be looking down at the collider. Where's my plate? That'll do, hopefully. All right, good enough. Let's see. Okay, and let me see if I can pin this. Okay, so hopefully that is pinned for you to see. And so what we're going to watch is, well, some of the things we just looked at. So Newton was saying that if one ball comes in and hits another one that is the same mass, then it totally transfers its momentum. And you can see how one comes to a stop and the other one moves off, right? So the momentum is getting transferred from one to the other. Now, it's not totally perfect after a while, but here it's pretty good. Okay, so there was that situation. The other situation was, what if they come in with kind of equal velocities? Okay, that was another situation you could test. All right, so they're exchanging momentums. And then let's see if I can do a one going faster hits another one moving more slowly. I don't know if I can do that, but let's try it. Okay, so here we go. Catching up, then one exchanges with the other. Okay, now, so when they have equal masses, the idea is that you have to have equal momentums in the ball that leaves. So the velocity is going to be equal. So let's say I just have one ball in and one ball goes out. I mean, it could be two balls going half the speed, but for an elastic collision, then it transfers the energy beautifully and the momentum. Okay, so what about two balls? Again, two balls in, two balls out, going the same speed. All right, so what about three balls? Well, you take three balls away, you've only got two, right? Seems impossible. So maybe they're going to go off with 1.5 times the velocity? Let's see. Nope. Three in, three out. Okay, so this happens with equal mass balls, and that's a lot of fun to test. Okay, so what about four? Yep, four in, four out. Okay, so these are as close to elastic collisions as you kind of can get. They do fade after a while because there is friction. And the stand shakes, so you don't get perfect frictionless collisions. And so the energy disappears, so gradually it winds down. But yeah, it's pretty good. Okay, let's go back. So let's unpin me. Okay, so now an inelastic collision is when you have an object that is colliding and momentum is conserved, but the energy isn't. These objects deform, they lose energy as heat as the pieces rub past each other or change its shape. The energy gets lost as vibration or sound. And so in the end, momentum is still conserved at the moment of the collision. It's transferred to the other object often, okay? And what happens afterwards, that's after the collision. And there might be interactions with the ground and other stuff. But momentum is conserved during the collision, but the energy gets lost to the environment. And by the way, these cars, everybody survived. This is what a modern wreck often looks like. The cars are totaled because the cars are made to fold in the engine compartment. And that's a good thing because the place where the passengers are is actually still whole. Okay, so that's incredibly great that people can survive these crashes because the engine block and the front of the car has crumpled. It has crumple zones, and that has made reduce the force, right? So it lengthens the time of the collision, reduces the force, and the people in the passenger compartment survive. Okay, now there's also a category called a completely inelastic collision or totally inelastic collision. In this case, what happens is that the objects stick together. So you can think about throwing a lump of clay at a wooden block, right? It would stick to it, but that would be a collision. And you might be able to throw hard enough that you're able to knock that block off the table or something. So the idea is that you can have a collision and the objects are coupled together or stick together and momentum is conserved. But again, some energy is lost, not all of it. So we often use the example of train cars because train cars start out usually about the same mass and they actually grab onto each other like this when they collide, right? That's how they're made. That's how train cars get hitched together. So they just collide them and at a slow speed and they latch together. Okay, so they're great for physics problems. So here we've got a train car, number one, the red one or the orange one, and it hits the green train car here. Okay, they collide, and afterwards they're moving together. That's the idea. They actually are now together. And so the formula, which before we had the formula, mass 1 V1 plus mass 2 V2 is going to equal mass 1 V final plus mass 2 V final, right? Well, that would still work, except we can take a shortcut. Because the velocities are the same, both of these cars have the same final velocity, right? They're both moving at 5 meters per second because they're hooked together. So because of that, we just can pull the masses out and multiply by the common velocity, which is V final is the same for both of them. We don't have individual velocities anymore. So anyway, so we just have one final velocity. So does that math work for this one? Why, yes, it will, of course. All right, so let's just go do that. Okay, so completely inelastic collisions. And so these train cars, one was coming in at 10, and the other one was sitting there at 0. So let's see if we can deduce that final velocity. Now, what about the masses? Well, let's just make them 1,000 kilograms, okay? All right, they're going to have equal masses. All right, so I'm going to make 1,000 kilograms for the first car, and it was moving at 10 meters per second. And the second one, so I'm kind of stretching it out here, is also 1,000 kilograms, but it was moving at 0, right? So that's the initial momentum. And that is just going to be due to the first train car. So that's going to be now 10,000 kilograms meters per second for the initial. Now, for the final, on the other side, we have to add the masses together. Now, they had the same mass. Mass 1 equals mass 2, which is 1,000 kilograms. Okay, so in this case, I can just use the formula. So the other side here is 1,000 plus 1,000 times some final velocity. All right, so what have I got here? I've got 10,000 on this side equals 2,000 times the final velocity. Divide both sides by 2,000. And I'm going to end up with the final velocity is equal to 5, right? And that will be velocity, so it'll come out to meters per second. Okay, so it worked out beautifully. Worked out just the same as we were told. It would come out to be 5 meters per second, and it did. Okay, so now why did it come out to be 5? Well, basically, they share the momentum now. Okay, so the first car came in with some momentum, and it shared it with the second one. Okay, so let's look at this with some more train cars. Okay, now here it comes in at 40. What will happen with the velocity? Well, again, same idea, right? It's coming in at 40, but it's still going to end up sharing with the other one. And so what happens is at the end, they have to have the same velocity. And so what's going to happen is we're going to end up with a velocity of 20, right? Go ahead and think about it. But yeah, the velocity is half as much because the mass has increased by 2, right? So the momentum has to stay the same. And so since the mass is doubled, then the velocity is half as much. Okay, so one goes up, the other one goes down. Okay, but the same amount of momentum before and after. Now, what happens if the masses aren't the same? So let's say we've got our train cars coming in at 40, and as it turns out, instead of being identical, one of the train cars is twice as much mass. Okay, so let's say that the green car has actually twice as much mass as the orange car. Okay, now, one thing is I don't actually have to tell you how much mass that is. I mean, I just did it a minute ago. I said it's the mass goes twice as much, but I didn't actually say the number for the mass. You don't really need to know that if you know the relationship. So we know the relationship here. We know that mass 2 is twice as much as mass 1. Okay, so when we start to put the numbers in, we've got mass 1 times 40. And then we've got mass 2, but mass 2 is twice as much as mass 1. And it's going at 0. Okay, so everything we're going to get comes from the first car. All the momentum comes from it. And we can just write it as 40m1. Okay, on the other side, I can write mass 1 plus mass 2 is, well, that's twice as much mass, right? And then there's some final velocity that I don't know. I'm just going to leave that as my unknown because I really don't know what it is. I can probably guess. Okay, so what have I got now? I've got 40 mass 1 is equal to m plus 2m is 3 mass 1 times V final. And so you see what's going to happen now. I'm going to divide both sides by 3m. And having picked a horrible number, 40 divided by 3 is going to be 13.3. And my mass 1s cancel, right? The mass 1 is gone. And so I end up with the final velocity is 13.3 meters per second. Okay, so you can figure things out without knowing the actual mass, if you know the relationship between the masses. Okay, so one way I like to figure this out is what I call the party. Okay, the party system. Let's go back to this original. Well, let's go back to this original one. Okay, let's say you were going to a party and one other person was at the party. You brought 10 cookies. The other person brought 0 cookies, but you're very nice. So you're going to share your cookies. And so you bring your 10 cookies and share them. Well, now there are 2 people, so that means that they each get 5 cookies, right? All right, so maybe you brought the cookies, he brought the pot stickers, but the idea is the cookies get shared and you end up with equal amounts of momentum in the end, which is like cookie mass. All right, so the same thing can happen with the one we were just doing. Someone brought 40 cookies to the party, but there were 2 people who brought no cookies to the party. Okay, they didn't bring any cookies, but maybe they brought pizza. Okay, so if we're fair, if there are 2 people plus 1 person, that's 3 people, and there are 40 cookies, so how many cookies do they end up with? 13.3. 333. Okay, so that's my cookie idea. You're bringing something, or you're not, to the party, and once it's there, it gets shared amongst all the other masses. Okay, and so that'll allow you to give you a way to think about it. So here's a freight car moving towards an identical one, and of course the speed is the same, is half as much, which we talked about before. So mass doubles, speed is half. Okay, now collisions can happen in reverse. We call those explosions. So it's when things are together and then they separate. Okay, so that could be like a bomb, but it could be anything else too, which starts together and then they push off each other to separate. So if you've ever had a cat leave your stomach by jumping off, then you know what a collision feels like in that case. Okay, so in this case, we've got a person who is 48 kilograms, the boy, and he's going to push off from his skating partner who has a mass of 40 kilograms, the girl. So they're pushing off from each other. And so we've got our before is here. We've got our after over here. And you can see they have pushed off and they now are going opposite directions. And they are going at different speeds, not the same speed, because they don't have the same mass. So they start off, though, with 0 momentum. This whole picture, this whole side, the left side, this has no momentum because they're standing still. Each of them has a velocity of 0, right? And they're together. So together, they have a velocity of 0. And so this whole side is just a big 0 because they're standing still. But on the other side, they're moving. You might think, where did that come from? Well, it comes from them pushing off each other. There's a force, and it pushes for a time, and it changes their momentum. Impulses change momentums. Okay, so anyway, so they push off with some amount of force. They change their momentum. And now, if we take the numbers She's 40 kilograms. She's moving at 3 meters per second. That is 120 kilogram meters per second. For the boy, he's going backwards, so we got to remember the negative sign. Okay, so backwards is negative. So for him, 48 times 2.5, guess what? That is also 120 kilogram meters per second, but it's negative because he's in the opposite direction. So when you add those back together, what's the total momentum? Well, the momentum is still 0. This side is 0 too. You started with 0 momentum, you end with 0 momentum. Even though both people are moving in the system, the momentum cancels out. So they started with 0, they're moving in opposite directions. The system of the boy and the girl still has 0 momentum. Okay, so anyway, so something to think about. All right, so that's the end of chapter 6.